So whenever they give birth, you could have it print out, for example. You could you're just putting a trace LN right there where they give birth. Yeah. Sorry. Oh, if you wanted it that way, you'd click on the transition to give birth, for example, and just in the code that says like baby equals such and person baby equals such and such, add connect to this, add to my child collection. You could just have it say trace LN, I just gave birth or whatever. Okay, so wherever you can put code, for the most part, put statements, then you can put that in. Okay. Okay, so folks, I'm going to do some fast footwork here to finish up this morning's session, so we can get over to our guest lecture for lunch. Pardon me as I just go through a couple of things. We've seen a bunch of things this morning. We saw some aspects of events. We saw some aspects of networks. I just want to talk about events here. So any logic is based, it's not exaggerated to say that any logic is built upon a very, very sophisticated system for handling events. Okay. So today we saw explicit event constructs being added to a model. Any logic, however, has many types of events that are captured. You have events when you send a message. You have events when a person goes from one state in a state chart to another, when a transition is fired, when we start and stop a model. There's an enormous number of implicit and explicit events which are associated with a model, and any logic jumps from event to event to handle each successive event when it occurs. It secures great operational efficiencies by not doing anything between most events, just going event to event to event. Much of the art of building any logic models is putting in code to deal with events that occur. Maybe it's arrival at a destination, maybe it's when a message is received, etc. We can also, as we saw this morning, introduce explicit events from the console. I talked about regular events here, which have a schedule associated with them, which go off at a certain rate, or go off at a certain time, or go off with a certain time between firings. But we can also have dynamic events, which basically allow you to sort of say, okay, an event should occur some amount of time from now, and give it all the information it needs to make it happen. So, for example, if you were simulating mule deer and you wanted to simulate pregnancies of mule deer, at the time of conception, you might schedule a birth of a deer some months from now, and have all the information given to it to perform that birth at that time. Okay, so it's quite common with these sort of events that we examined today for them to go off at a specified rate, to go off on a one-time basis, cyclically with some fixed time, or when some condition changes, for example. So I'm not going to talk about dynamic events, but you'll find a lecture by me online where I do talk about the use of dynamic events, which are quite useful in certain specialized circumstances. For the most part, the events that we use today, like that immigration event, to have people immigrate at a certain time, are going to be what you're using most frequently. I should note that events can take place. The immigration event, where did that live? In this morning's lesson, where did the immigration event live? It lived in Maine. We can also have events at the person level. So an event that occurs for each person. Give me an example of a sort of event that might occur on a per-person basis. What might happen on a per-person basis as an event? Something, say, that occurs periodically, every year at exactly a certain date. It's their birthday. Yeah, exactly. Another event that might occur on a per-person basis would be, an event simulating the occurrence of an accident with a certain low probability or what have you. So we can have events that operate at the individual level. We can have events that operate in main, okay, at the level of the entire model. So scheduling events using this sort of event construct in any logic is par for the course for sort of building up models. It's an important building block when you're building models, and immigration is a great example of an event that can be scheduled. Okay, in general, sometimes you'll create these explicit events. In many cases, the things of interest, the incidents of interest, will be triggered by state charts or triggered by other constructs within the model, and you don't need a formal event for it. An example would be birth or pregnancy events, etc. We don't need to put in an event per se. We can just have a state chart that handles that. Okay, so that's a few remarks on events to better understand what we did there. Be aware that any logic has a wide variety of types of events here. So, excuse me, they can go off at one time, specified rate, cyclically, etc. We can set events in any logic that go off on a calendar as well. Any logic has a very powerful notion of maintaining an actual calendar schedule that takes into account leap years and leap days and days of the week and all those sort of things. This sometimes will be useful for you if you're actually trying to simulate out in a very detailed way a calendar of events. You can ask, is this a weekend or weekday, for places where it's useful to do so. And you can set an event to go off at a certain day at a certain time, for example. Okay, so those are events. Just a little bit more background on what we saw this morning. I'd like now to provide a little bit of additional background on networks. So we have seen within our models one type of network. We saw a network that was distance-based. In other words, people were connected to each other if they lay within a certain distance of each other. Two people are connected if they say lay within a distance of 50 of one another. And this is defined by the environment. The environment lays out spatial characteristics, whether we consider space continuous or discrete, whether we make use of a network, and we can make use of several network types, and as well several neighborhoods for discrete space. I'm not going to have time to go into these things in great deal of detail here, but in any logic, there's several types of networks supported. Distance-based was the type that we used. You can also have a ring lattice or a small world or a scale-free network, as well as a random network, what might be called an Erdos random network, a Poisson random network, or a Bernoulli network. You'll hear those are all names for this type of random network. You can further define what layouts to use for the agents in space, whether if we have fixed agent locations, should they be randomly placed, as we've dealt with thus far? Should they be arranged in some sort of grid? Should they be placed in a ring? Or should they be laid out in such a way that a network tries to place people who are connected close to each other? Okay, so we have these layouts, and then we have networks associated. We have certain types of networks as well. These two interact to a certain degree. So, for example, a distance-based network has people connected if they are located within a certain distance of each other. So location dictates network. And then there's a type of layout called a spring mass layout where who's connected dictates where people are placed in space. Okay, so we have spatial layouts and we have networks, and they have certain interaction for certain types of situations. So when we have a network, that dictates who is logically connected with who. And we could lay that out in any number of different ways. For example, we could have a ring lattice network. Each person is connected to two neighboring individuals. And everyone is ultimately in a ring. But we could lay it out in space in kind of a jumbled fashion, or we could lay it out in a ring like that. And any logic allows you to, through different layouts, to do either one. It's the same logical structure. They're just laid out differently, okay? And same thing with a random network. Here we're connecting any two people regardless of location, for example. A random network will tend to have behavior in terms of infection spread that is not too different from random mixing assumptions. If you have enough connections per person, you tend to get some behavior similar to if you assumed everyone in the population is bumping into one another, okay? We also have small world networks, which are sort of weighted combinations of a very localized network where people are connected just to people nearby them, like this, and a network where people are connected to random people around, okay? These are very, very easy to experiment with in any logic. I guess I'd like to suggest here that you consider opening up here. Time will be short, but if you want to open up in your O drive a model called minimalist SIR network-based ABM here. So if we go to the O drive, minimalist network SAR network ABM. Okay, SAR network ABM. And we'll experiment with this just a little bit before we're going to lunch. So here we have a situation where we have persons are susceptible, infected, and recovered, and we have people in a network as specified by the environment. Okay, so the population. Remember, in the population we say what's the environment that manages the networks, manages the spatial location, and in the environment under the advanced tabs we can specify what sort of network to use. So I'm going to run this model right now with the default network type, which is a distance-based network. And here we have individuals within a distance-based network being connected up. You notice this is with some reporting going on as well. I'd like, however, to go try different networks here. So where would I go to set different networks for this? Where do I go based on what we've just said? Environment and advanced and, okay, the network type and the layout. So the layout will be where people are placed in space. The network type is who's connected with who. So for the first one, I'd like to suggest doing a random network. We just saw a distance-based network. Let's do a random network, see how things differ there. So I'm going to run this now with a random network, and now people are connected willy-nilly. So if you take a pair of people, they have an equal probability of being connected, regardless of the other people to whom they're connected. There's a certain chance per unit time they'll be connected. And here you'll see actually the infection spreads much, much faster than it did with that distance-based layout. Why is that? Why would an infection spread across this population much faster when they're connected willy-nilly compared to when they're only connected with neighbors? Anyone?
Because the average distance between somebody who's far away in the space is
Yeah.
much larger.
Exactly. So with a distance-based connection, the infection has to propagate incrementally over the space to reach from me to someone across the country. It has to sort of reach successively across the country, whereas in networks they're very local. Whereas in a random network, it may be that I'm connected with someone who flies to California every day, and so they serve as a conduit for a connection very rapidly. Okay, so we've just seen a random network. Let's You'll notice, incidentally, when I selected random network, that it allowed me to fill in connections per agent here. I'd like now to take the exact opposite. A random network is a global network. You're connected with people regardless of position. There's no preference for people who are local. Now let's try a ring lattice network with the same number of connections per agent. Now let's see how that infection spreads for that network. Okay, so here we're declaratively changing the agent type, and we're running this out. You'll notice the infection spreads much more slowly. This is an extreme of locality. It spreads very, very slowly because it is highly locally connected. Now, people, when I ran that here, you'll notice that the locality of this network is not obvious. So if I want to see this network and see its structure clearly laid out, what I'll want to do is I'll want to lay it out in a ring. So I go to network, I go to environment and advanced, and I choose the layout type, choose it to be a ring, okay? And if I lay it out in a ring sort of way, then I'll see it nicely laid out in structure, and you can see how it spreads in a very sort of localized way. Let's try that again. I'll try running that again with a spring layout. In other words, with the layout type being a ring layout. And you'll notice it's spreading out from this point in a very gradual sort of way. Okay. What do people think a random network would look like in a ring like this? Can anyone comment? So remember, the layout defines the spatial location. The network type defines who's connected with whom. So if I showed, what I'm showing here is a ring lattice network with a ring connection. Let's suppose that I were to impose a randomly connected network. In other words, an Erdos random graph or a Bernoulli network or a Poisson random network. You can use any term for it. What would that look like if I laid it out in this ring? Okay, good. So let's go do that. Let's retain this layout of a ring, but let's go do that for a random network and run it here. And what we see is something like that. People are connected willy-nilly across the network. And as a result, infection that starts one place can zip across the network, just as Davoud was saying, and colonize an area across the network entirely, such that it spreads very quickly across the entirety of the network. Okay, so that's good. We have several other types of networks as well. The small world one is a mixture of a ring lattice on the one hand and a Poisson random network on the other. So this neighbor link fraction, that gives the fraction it's kind of a weighted combination of the two. This is the weighting associated with the ring lattice network. So what would we expect to see if this is sort of 95% a ring lattice and just 5% a Poisson random network? What would we expect to see if we run it in a ring type of way? What would we see? If it's mostly a ring lattice network and only 5% is a random network, what would we expect to see when we lay it out in a ring? Well, predominantly it's connected in a ring type of fashion, and there's a few connections that are at a longer distance here. The big insight, though, from early network work was that even just having a few connections of this sort would allow it to spread quickly, because it would spread up to here, and then it could zip across here, and then it could zip across there. And actually, it can end up spreading overall very, very quickly with only a fairly small fraction of global connections. Okay, let's try a few others here. So in the environment, we'll try a we'll try a scale-free network. Now, a scale-free network is a network where you'll find my online lectures. I have a whole lecture devoted to scale-free networks in particular. They exhibit long tails associated with the number of connections a given person has. And they're often associated with the desire to capture great heterogeneity in contact rates, for example, between people. They have power law distributions associated with the number of connections a given individual has. Most people have very few connections, but some people have a lot of connections, okay? In this case, wow, we have a lot of connections. I must not have left the number of connections to be normalized the number of connections with that. So we'll downplay this M parameter, which you'll find it's approximately double the average number of connections per person, I think. Here, some individuals have many, but many individuals have quite a bit fewer. So here we have some individuals that are very dominant in terms of the connections, but many people who have small numbers. And this M parameter, you can find some of my online lectures where I comment on it and have some lecture notes on its meaning. Okay. Okay, so we've seen different types of networks that any logic can enforce. You can also, of course, wire your own networks. And I have several example models where I show how you can read in data from files, for example, and build your own networks, either static networks or dynamic networks that are changing over time, or that are just built up front from a file. So if you have some network information in PIAC, for example, for social network analysis, and you want to bring it into any logic, I have some code that can read basic PIAC files and put that network into any logic in such a way that it could then simulate dynamics on those networks. Okay. So these are several network types created by any logic, but in a nod to our lecture, well, any questions on this before I sort of presage our guest lecture for lunch? Yes? Sure. Okay. So there's, as you may or may not know, there's a lot of, there's a tremendous amount of grounded network theory. So Mark Newman and Barabasi and others have sort of laid this real conceptual foundation for understanding networks. Steve Strogatz, Duncan Watts, and others have contributed a lot. And there's many empirical cases where, for example, network structure is well described by certain parametric types of networks, say by a ring lattice network, say by a scale-free network, or say by a network which is a small world network of other sorts. And so we have data that we've collected empirically, for example, which exhibits some properties in terms of power law distributions, more similar to a scale-free network or other members of class of small world networks. And it turns out that the network type often will have a really large impact on phenomena on that network, dynamics on the network. For example, the spread of contagion. Maybe it's ideas, innovations, maybe it's pathogen spreading across that network. At the same time, so sometimes you use a network type here that's informed by empirical data that you had, and you want to understand for that type of network what's the implications for spread. But sometimes you want to understand, for alternative network structures, how would those dynamics be different? For example, if we were dealing with a more localized flow of information rather than more global, how might that impact the contagion process and then for percolation or what have you? being able to flexibly switch between different types of networks is often useful. For a lot of our applications, we end up building our own networks from empirical data that we have, and we impose them here. We've actually seen how you can do some of that this morning. Remember, we added a connection from mom to baby, for example. That's sort of maybe the most simple example of building a network, connecting two people up. And so I find that these type of multiple networks are really useful for experimentation on a sort of quick basis. But for a lot of our work, we just build our own network structures. So I don't know, that partly addresses your question. Yeah.
Do you build any networks with AF and
Vensum would not have suitable tools for networks. Network connectivity in Vensum will have imposed that. It tends to be very poorly supported in a system dynamics modeling package like that for two reasons. One, it's mostly used at a higher level, and two, differential equations can make use of network connectivity, but it's done in pretty awkward ways typically with subscripting. But Payek, for example, is a great place to build up networks. UCINet, there's others as well, and as I mentioned, Payek files can be imported into any logic. And in general, if you have a UCINet file and you've had a bit of time from someone from computer background in a day or two, they could probably create a controller that is really active. So that's readily done. Which type of network you use will depend a lot on your research question and context. For example, road networks are going to exhibit connectivity that are more distance-based. So a lot of distance-based connections between neighboring cities and so on. Scale-free networks you'll see emerge in other areas. So which networks are most relevant will depend on your research area. Having some flexibility to quickly change network type for experimentation can be helpful for developing intuition about how network characteristics affect the dynamics you're seeing in the model. But often I find that if you have a model that aspires to be really empirically grounded, importing your own is often desirable. And you can also use, like Winchell here, has also done a bunch with using dynamic networks with this. So you have the network changing over time. And again, I have some code to do that with network specification from files. Okay, any other questions on that? Yes. I'm sorry?
You said you had code
Yeah.
and example models, but that was
Yes, those are part of the set here. So for Payek, pardon me for just a second here. So it's file-driven network structure, successive examples. I have a minimalist network ABM model with file-driven network structure, so that can import, for example, some of those. They all have mechanisms for importing, for example, from Payek. Okay, any other questions? Okay, so we're going to have to go to the faculty club here in just a minute. I'd like to presage what we're going to be seeing by just pointing out the fact that while we've got this model open, there's a whole other area of the environment that's provided here. You'll notice up at the top, you could specify the space type, whether this is a continuous 2D space, or excuse me, a continuous space in 2 or 3 dimensions, or a discrete space in 2 or 3 dimensions. AnyLogic supports a variety of embedding types, and also supports mobility over those spaces. So we can embed agents, for example, to capture dynamics of local transmission over space, and to understand spatial patterns of the sort we saw in the very first model we used in the workshop. And this sort of spatial embedding can permit some linking with GIS data. There's two basic models that are used for spatial embedding. One is continuous embedding, where we have basically agents who are assumed to be very small in relation to the landscape scale. They can sort of pass each other without conflict, and they move in a continuous way across that landscape scale. Think of a car driving from the perspective of a satellite photo, sort of moves along in a smooth way along in continuous space. By contrast, some models make use of discretization of the space into cells of sorts. We saw this in the very first model that we had, where we had this very stylized space. People were arranged in a grid. They could communicate with people north, south, east, and west. In principle, it could be done with all 8 directions. And we have only 1 or 0 people in a given cell. The space is divided into columns and rows in addition to sort of having a spatial location. And the analogic environment is, again, critical to this. So with the continuous environment, you specify the width and the height of the space, and then you can, and we've in fact been using that without realizing it. Our agents have been placed in a continuous space. They have not been moving around, but they have been situated there. And by contrast, the discrete environment has columns and rows associated with it. And so, for example, the classic game of life, where we have cells sort of playing out over time, and you have something like this. So-called cellular automata fall into this category. And so this space here might represent a very regularized environment of some sort, and you get interactions. The Schelling segregation model is also a model like this, with the added proviso that there's mobility of agents. Now, when we do have an agent space which is continuous, and I'm just going to, this is again sort of in preparation for this lecture, we can move people around, and we'll have some exercises to do this following lunch. But we can move people around, and oh man, I thought I had a nice illustration of this, but oh boy, we're gonna have to wait for the lecture at lunch. But people can move in a way that's continuous. And so, just to impose this on the model that we have open right now, I'm going to set the person. I'm going to take the person here, looking at their, when I click on them, I am going to set them off moving in a direction. So on click here, I'm going to do this dot move to, and I will pick a random spot within space. So I'll draw from a uniform distribution in continuous space from 0 to 500. If this were real code, I would actually look at the size of the space and go from 0 to the size of the space. And so if you'll notice this person is now moving, and they are moving to some destination, and I can click on other people, and they'll start moving around and migrating in the space. Now, I'm not adjusting the network, so it looks kind of odd right now. I would have to reform the network and have the connections go accordingly. But this is an example of agent mobility. And in general, AnyLogic provides a very simple way to have many agents in movement at the same time and interacting in space through that. Some of the examples, the exercises we've laid out for you do involve movement in space and collisions between agents, for example. And AnyLogic makes this quite simple. You simply say, this agent, start moving towards that space, and when they arrive, an action can be triggered in them, which will let them do something good. Okay. So it automatically takes care of keeping them updated, updating their location until they arrive, and then it tells you they've arrived, and you can do something based on that. So what we're going to see now, as we go over when we go over the faculty club, is a talk which builds atop these capabilities of any logic in a continuous 2D environment, but with some additional information with discrete ties like vegetation, etc., and use of that for understanding infectious disease transmission due to environmental exposure. Okay, so let's go over to the faculty club now, and we can see this guest lecture. I'd suggest that as soon as we arrive, we go and get our dinner, and we can settle down and watch the talk then. Thanks.